All right, everybody, we have a request to do Fall 19 Test 4, Part 1. The scheme is of particular interest this time round. And what we have here is a alcohol with a stereocenter on carbon 4 and a double bond on carbon 1. Let's draw it. There's 1 and 2, 3, 4, 5, 6, 7, 8. The 4, 1, 2, 3, 4 is an S stereocenter, which puts the OH on a wedge and the H on a dash. So that is our starting alcohol for every single problem. And what's going to happen here is osmium VIII oxide, that's OSO4, is going to react. And in the presence of a peroxide, we get a vicinal diol right here. So what we're going to show is the vicinal diol, product 1, over here by product 1. And the good stuff's over here. And because there's no changes over here, I'm just going to label that as R. That's R. And you're going to get a 50-50 mixture of two molecules, OH on wedge. And I'll show it on a wedge here, although it's kind of silly on a CH2. That's half of them, and the other half is the enantiomer. Oh, careful with your words, Dr. Whitaker. There's a stereocenter in R that will not change during this reaction. So we're not going to make an enantiomer, we're going to make diastereomers. Because we have a new stereocenter here. And in this particular one, it's S. And in our enantiomer, so enantiomer, it will be, this one's S, and S is in the R group, and the enantiomer is going to be R with S in the R group. So
my question is,
yes.
Isn't the osmium oxide is what added the diol instead of the which like broke the alkene and just added the diol? So
Yes.
what did the peroxide do?
The peroxide makes osmium VII oxide into a catalyst. So what it does is it generates an osmate ester with osmium up here, and then it gets broken down by the peroxide back to osmium 04.
Oh, okay.
So that's the only role of that.
Okay.
It breaks down the ester and regenerates the catalyst.
Oh, I see.
So we're looking for molecules that have 1, 2, and then carbon 4 is still an alcohol. So 1, 2, 4 triols are all across here. We're going to have SS, and that's S on carbon number 2. And this is number 4, the old one. And number 2 and number 4 is here. So SSRS, SSRS, we have RS, and we have SS. So it'll be a 50-50 mix of 3 and 4. So that's your answer there. Moving down here for product 2, your alcohol in R group is going to be converted to a toluene sulfonate ester. The most important thing here is the stereocenter stays S. This just puts an ester on the alcohol. So I'll just show step 1.
So that's something we can memorize, like paratoluene sulfonyl.
Oh, you have to know if you know the mechanism, then yes, you've memorized it. If you don't know the mechanism, then it's just straight memorizing.
Okay.
Because there's not a backside attack in that mechanism on the carbon. There's only a backside attack on a sulfur to make the ester. So in this one, we'll go with I don't know, let's go with baby blue. Step 1 here going down here. Step 1 generates this species here. And it's still a wedge O. And we don't have to show the TS drawn out. And you get that. And then we're going to do an SN2. You know how I know it's an SN2? It's because we have a secondary RX. We have a strong nu. And we have a polar aprotic solvent. Those last two items, the nucleophile and the polar aprotic solvent, guarantee SN2. So we're going to go from an S here in step 2 to our final product, which will be product 2, looking like this. And that will be a cyanide on a dash. The most important thing is you don't really have to draw it, is to know that it's a backside attack on an S stereocenter giving an R stereocenter. So R4-cyano 1-octene. R4-cyano 1-octene is this one, but that's not one of our answers. That's says 3 only is our answer. There we go. You don't get a mixture in an SN2 reaction, that's for sure. Probably have a mixture in an SN1 reaction coming up soon. We'll see. And by the way, that was step 2 that created that species. Step 2 generated this species here. Moving on. Phosphorus tribromide, we have to learn switches an S stereocentered alcohol into an R stereocentered bromine. So we'll do that one here. Step 1. Step 1, generating whoops, got a little carried away there. And one more. To a BR on a dash. Step 2 is going to do a backside attack using ammonia. And how do I know it's going to do a backside attack in ammonia? I don't. In fact, I'm wrong. Heavens. Do your analysis, Dr. Whitaker, just like you did before. What do we have here? Step 2. Here's your analysis. You got the same secondary RX. I'm not going to repeat myself there. That's a SN1, SN2. I don't know. Ammonia is both the moderate nucleophile, which means SN1, SN2. I still don't know. But it's also a polar protic solvent, which is SN1. So the only thing making your decision is the solvent. Ammonia is going to generate this 50-50. So I'm just going to show 50-50 here. NH3 plus RS, I'll just put there, because that's what an SN1 does, gets a mixture. And then the base is just going to take the H off. And as you might have guessed, taking H off an ammonium ion generates an amine. That's just an acid base at the end. So 50-50 mixture, but I think I have the wrong amine because I said SN1, didn't I? SN1. SN1, what's the intermediate that I have to keep in mind here? Intermediate in an SN1 reaction.
Carbocation.
Carbocation. Gives us a big BUT. There's the cation. If I move an H,
Allylic.
yes, she noticed there is now an avenue to get to a very nice secondary allylic cation by way of hydrogen shift. So we're still working towards product 3. I got a situation that happened on the way to product 3 that made a better cation. So I don't like the amine 2, 4, 6, 8. There's a cation here. That's allylic, secondary allylic. That's even better than tertiary. We know that. So the same logic holds. You're going to get an ammonium there. 2 and 3. Finishing up 2, and then acid base for 3. And here's your product 3. And the ammonium is here. The ammonium in step 2 becomes an amine in step 3, which is on carbon 3. So these didn't have the rearrangement, the ones with 4. And because it was SN1 and a carbocation was involved, you're going to get a 50-50 mix of 1 and 2. And that's answer E. And then moving on to the final deal here. Just like PBr3, phosphorus tribromide, gives a bromide where you used to have an alcohol, thionyl chloride gives, with pyridine, gives the chlorine where you used to have the alcohol, and a backside flip. So yeah, we got to know that mechanism too. So step 1 generates what is drawn right underneath. Step 1. You got the dash to the Cl. And then you're going to do an SN2. Well, how do I know an SN2? This is a little sneaky here. I don't know if I'm going to, yours is more straightforward than this. I got 2 pieces of information that contradict themselves. I got sodium methoxide, a strong nucleophile. That's NaOCH3 if you're keeping score. But I also have a solvent that allows cations. It's a protic solvent, methanol. And because I have an avenue to a very stable secondary allylic cation, which is more stable than tertiary, that's going to take over. So I don't like this one. It's too involved. Yours, I tried to make more straightforward. So I would have these 2 agreeing with each other, either both be for SN2 or both be for SN1 to make this, I don't know, fairer, less intricate question. But for the purpose of this exam on this particular date, this is letting the cation happen, which becomes a very nice cation right there. You're going to get the OCH3 on the 3rd position, not the 4th.
If we didn't have that allylic rearrangement, that wouldn't happen.
If you had a solvent like hexane or any of the solvents that lead to SN2, you do a straight up SN2. If I switch this to a HOCH3, which is methanol, and have just methanol, then you're going to go with what I just drew here, which is a racemic mixture of the methoxy on position 3. And that's what we're looking for, a racemic mixture with a methoxy on 3. And I only gave one of the 3. Oh, I gave both R and S. So this one's A and B. Sorry. Oh, which choice best represents 4? Wow. I don't even have the right answer to my own question here. I tell you I didn't like it. It's A and B for that solvent. So let's not stress out too much about this. Yours is going to be more straightforward than that one, I promise. And should we call this a segment or try the next one that's in the same video? They're almost the same, so let's do it.
Yeah, let's do it.
Yeah. R3 heptanol. There's no double bond in this one. 1, 2, 3, 4, 5, 6, 7. And R3 heptanol. We've got an H there and an OH there. Wedge. Not letting me draw the wedge. Anyway, I got carried away there. Let's go product 1, 2, 3, 4 again. Thionyl chloride gives a flipped alkyl chloride instead of an alcohol on position 3. So I won't be drawing all the intermediates this time. We start with R. Step 1 is going to give S attached to Cl. I don't know if that makes sense. S stereocenter with a Cl attached. Sodium hydroxide is both a strong nucleophile or a strong base, especially in the presence of 200 degrees Celsius. That's heat. Strong base and heat, E2 time. And we want, what do we want? We want major minor. We'll see. And we want major minor. Because you're going to get alkenes, right?
Yeah.
You're not just going to get one alkene. You're going to get, let's see, I could have got a 2-heptene, but it wasn't listed as one of the products. So don't worry about 2-heptene. The 3-heptene is by taking this H here. I'll just put a little note here. In the next step, this is the H that's going to go. So it's, you know, the one with the H attached here, which is beta. You can't do an E2 on an alcohol. You can do an E2 on a alkyl chloride. And you're going to double bond there with E being major, and Z being minor. There's steric hindrance in the Z. So 4 major, 3 minor, there's your answer. All right, now this one I'm just testing to see if you know what happens with chromic acid, because chromium 6 oxide reacts with sulfuric acid and water to make H2CrO4 as a chromic acid, and alcohols that are secondary with chromic acid become, yes, ketones. No stereocenter. No rearrangements, nothing. Straight up ketone where you used to have an alcohol, 3-heptanone, 4 only here. There we go. This one gave 2 alkenes. Okay. And what are we doing in this one? Oh, we're gonna do some sodium acetylide. Yeah, we can never forget what acetylide looks like. Step 2, this is what I was talking about on that previous one. Step 2 leaves nothing to the imagination.
Okay.
Strong nucleophile, polar aprotic solvent, both say SN2. But what's in step 1? Step 1, you're converting the alcohol from an R alcohol to an S BR. So step 1, I'm going to kind of do what I did before. Goes to an S stereocenter with a BR attached. Backside attack during an SN2 is going to give an R with an acetylide on there. So let's draw what we get for product 3 downstairs. 1, 2, 3, 4, 5, 6, 7. I think I drew 8 before out of habit. 2, 4, 6, 8. Yeah, from my previous example, I got used to drawing 8, didn't I? There we go. 2, 4, 6, 7. Good. And you're going to be back to your original stereocenter after 2 SN2s. You got to flip with the. In the first reaction, you got to flip, and the second one, you got to flip. You're back to R. And here's your new group. CCCH. UPAC says 1, 2, 3, 4, 6, 7. 3-ethyl 1-heptine with a what stereocenter? It's R. 3-ethyl 1-heptine. Right there.
Yeah, there's only one answer with R anyway.
That's correct. Yeah, there's your giveaway right there. You didn't have to. You got to stop thinking as soon as you saw the right one with an R stereocenter. Nice job. Product 4. What's going on? We're doing the Paratoluene sulfonyl chloride. Hey, from our previous example, we remembered that converted an alcohol to a tosylate ester with the same stereocenter. HO is kept, and we have a TS on it now. And it's still R, sorry, I might have said S by mistake. Still R, it started R, it ended R, because you did the attack on sulfur, not on this carbon. And then the next one, I made it very clear, so I'm happier with this example than the previous one, with that number 4 than being so sneaky. OH minus, I just write strong, I'm just gonna say it, I'm not even gonna write it. Strong nucleophile again, or a strong base, but there's no heat this time, so just strong nucleophile. Polar A product solvent again. So this is gonna hit the backside of the R stereocenter and generate an S alcohol. I'll draw it down here. Yes, the new group is OH. And it'll be S. So the OH is on a wedge. And the H is on a dash. So I want the S3 heptanol. That's B only. And that's good. Lots of schemes. I think you found one more scheme, didn't you? It was a 2. I don't remember. We have another scheme waiting for us here, and they're all related. Wow, this one even starts with the same molecule. Did I grab the same thing twice by mistake? No, I did not. Oh, wow. Okay. All right. So this is good. Let's just stay on the screen here. R3 heptanol, 2467. You got an H here and an OH here. And thionyl chloride goes from an R stereocenter to, this is step 1, gives an S, where there was an OH is now attached to a Cl. And then sodium cyanide is strong nucleophile, acetone, polar A product solvent. You're going to go to an R to a cyanide on the same carbon. So some kind of R cyano. Ah, there we have it. Groovy. R should be in, it's a stereo center we're talking about, not an R group. And that's the answer. Which choice represents product 2? This is hots and heat. Hot. I like that. I'm sorry. You got to put up with me sometimes. Hots and heat is hot. Hey, this is the conditions for the acid catalyzed dehydration of an alcohol. Wow. Hots and heat. And I want to pick, it says which choice represents products 2. Well, it doesn't have anything about major or minor listed in any of the products. So I guess I'm only looking for 2 major products here, or 1. If you think there's just 1 forming, but there's no distinction in stability between this one, where I took the beta H, that's too many carbons, 2, 4, 6, 7, yeah. I took the beta H from the left of the alcohol. I'll just remind you here what's going on. After you protonate the alcohol, it's a leaving group, and you got a beta H here, and you got a beta H here. Those are both candidates for doing your E elimination. So there's one of your products, 50%. That's getting it from the left. Trans is more stable than cis. And getting it from the right, you get this one, 50%. One of them starts on carbon 2, one of them starts on carbon 3, 50-50 EE. So I like AB, which is 50-50 E, 2 heptene or 3 heptene. You're going to get roughly the same amount of each one.
We don't get Z.
You'll get Z. Yes, you will. Those will be minor.
Okay, so we assume that you were asking for the major.
Often it depends on how I ask the question, doesn't it? Oh, did I also do the wrong product there? I did, didn't I? That's the wrong question. Let's just move my circle. If it lets me. There. There we go. All right. So let's be clear here. Need my pen. Let's keep this separate from the next question. Product 3. Product 3. Well, step 1 in going towards product 3 converts to a S-alkyl bromide. S stereo center with a bromine on it. And a secondary, so that you're not using that to decide this next part, which has a strong nucleophile, could also be a strong base, but there's no heat, so I don't care. It's a strong nucleophile only, and a polar aprotic solvent. SN2, SN2, this is an SN2. You're gonna have O-ethyl attached where the bromine used to be. Product 3 looks like this. And I'm just going to do it this way. We have a O-ethyl, and the stereo center is going to be S. So which product looks like that? It looks like B, S3-ethoxy heptane. So that's that one. Product 3 only. No, sorry, 2 only. 3 is an E2 product. We don't want E2 products in this one. If I change this to have heat here, yeah, E2 it would be the same answer as the previous question. If I added heat in this one, just, hey, still a good question. Add heat with a strong base, you're going to get E2. And what else you got? Paratoluene sulfonyl chloride. Seem to be asking the same questions over and over. That's good stuff. These are all good reactions, that's why. So step 1, you get your OTS with the same stereo center. 2, 4, 6, 7. It's still an R stereo center with an OTS on it. TS. So now it's an RX. And you're going to hit it with sodium acetylide. That's that strong nucleophile, and a polar aprotic solvent. It's going to go to S. Again, with a C-triple-CH there. Keep these separate. Draw the product right under here. Carbon 3 will be an S stereo center with a C-triple-C on it. Probably don't need to draw it. Probably figure it out. Not the nicest drawing there. It has to be S or else it's wrong. And S3 heptyl 1 heptine looks like it. 1, 2, 3, 4, 5, 6, 7. Yep. B only again. Oh, sorry, 2 only. S3 heptyl 1 heptine. I think we have a pretty lengthy video, unless you have some last minute questions.
On the answer key, 13 was put as 1. That must be wrong, right?
Oh, did Dr. Whitaker forget the stereo center stays the same when you make a tosylate ester? Yeah, he did. So there's a typo on the answer key. We're gonna make it. I'm trusting you on this one. Control T. Typo on. Typoon. Okay. Typo on answer key. This is the right answer. And here we go. Move that to where it belongs. The big orange, cautionary orange. There we go. Okay, thank you for clarifying that. And I think this should be helpful to a lot of students. And we'll come back with our little preview here. We'll do sadly a COVID roadmap where there's no boxes because students didn't all have printers. That's why. But you know, we'll pretend these are all boxes, okay? And we'll come back and do this.
Okay.
All right. See you soon.